There we go. There we go. Anything else you want me to do? So we're developing some rules for finding derivatives in section 3.2. We have that the derivative of a constant is 0. So I write that like this: the derivative of a constant is 0. The derivative of x to a power is found by bringing the power down, raise that expression to 1 power less. The derivative with respect to x of a constant times a function of x is that constant times the derivative of the function. And then you can also do things term by term. Derivative of two things that are added or subtracted is done like that. But that does not hold for things that are multiplied or divided. So I guess that's what I'm going to do today. Show you what to do with things multiplied and divided. First, example. So for example, if y is equal to 6x to the 1/3 plus 4 divided by x squared minus pi, and our goal is to take the derivative of that, then what we want to do is write them as terms that look like x to a power, added and subtracted from each other. So I'm going to take that 4 over x squared and I'm going to rewrite it before I take the derivative of it. I'm going to write that as 4 times x to the -2. Then we're going to use a combination of these two rules. Let's say we do things term by term, ignore the constants, take the derivative of the expression involving the x, move through the plus and minus signs. So here I'm going to take the derivative of 6x to the 1/3 by bringing a 6 out. And now our power rule. We bring the 1/3 down, we raise x to 1 power less. So I'll do that in the next step. Same thing with the middle term. Keep the 4 out of the way, bring the -2 down, raise this to 1 power less. Then finally out here at the end, recognize that pi is a constant and the derivative of any constant is 0. And now simplify. 6 times 1/3 will give me 2. 1/3 minus 1 will give me a power of -2/3 on the x. 4 times -2 is -8. -2 minus 1 gives me -3 as the power on the x, and then I don't need to write the 0. And maybe it looks a little bit better to write that as 2 over x to the 2/3 minus 8 over x cubed. And there's our derivative. So for instance, if I wanted to know what is the slope of the tangent line to this graph when x is 1, well, then I can go down here and put a 1 in for x, and I would get 2 minus 8 is a negative 6. Okay. How about I have you write an equation of a tangent line? Right? An equation of the tangent line to the graph f of x is equal to about 10. How about I need a number divisible by 3. Let's make that an 18. 18 over the square root of x at the point where x is equal to 9. Equation of the tangent line to that graph at the point where x is equal to 9. It's just too big. To write the equation of a line, you need 2 things. You need to know the slope of the line. And what else? Maybe the y-intercept, but any point will do, actually. Right? You need an ordered pair, and I only gave you the x coordinate. So can anybody tell me what the y value is when x is 9? It is 6. You put 9 in for x, and you get 6. 18 divided by the square root of 9. First, when x equals 9, y is equal to 18 over the square root of 9. So y is 18 over 3 is 6. So I've got the ordered pair 3, 9. That's going to be my x1 and my y1. Now we need the slope. So I want you to rewrite that first as x to a power, and then I want you to take the derivative using our power rule. To square root sign is what kind of power? 1/2. Move it upstairs, and it becomes 18 times x to the negative 1/2. Take the derivative and write the derivative with positive exponents. So did you get this for your derivative? 18 here. The -1/2 comes down in front. Then I'm going to have this to the 1 power less. What'd you get when you took 1 away from -1/2? -3/2. So let me put this step in here. That's 9x to the -3/2. The 9 doesn't have the power on it, so it stays on top, but the x goes on the bottom to the 3/2 power. So now we've got to figure out what 9 to the 3/2 power is. Just like before, the bottom number means a square root. So we do that first. We take the square root of 9. And then take that number and raise it to the 3rd power. Square root of 9 is 3. 3 cubed is 27. So I have a -9/27. And that simplifies to a -1/3 is your slope. And so now the equation of the tangent line looks like y minus y1 is equal to m times x minus x1. And so we have y minus, where's my y1? 6 is equal to -1/3 x minus 9. You can leave it there. You can move the 6 over. Doesn't matter to me what it looks like from here. Okay. Okay. So now, I want you to note that the derivative of a product is not the product of the derivatives. By looking at something kind of easy. Let's look at multiplying x squared with x cubed. What do you do with the powers? You add them. So this is the same thing as saying x to the 5th. So the derivative of x squared times x cubed should be the same as the derivative of x to the 5th. The derivative of x to the 5th is 5x to the 4th. But if we individually took the derivative of x squared and then multiplied it with the derivative of x cubed, we're not going to come anywhere close to the 5x to the 4th. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. Multiply those together and we get 6x to the 3rd. So that doesn't do us a dang bit of good. We can't take the derivative through a product. We can only take the derivative term by term through a sum or a difference. We can't take the derivative through a product. Dang, that's starting to tick me off. little bit smaller. There we go. Maybe too small. How about that? So what I'm going to do next is derive for you a product rule. Then we're going to do the same thing when we have an x on top and an x on the bottom. We'll do a quotient rule. So I'm going to let, this is the derivation of the product rule. I'm going to define my function little f of x to be a product of two terms, capital F for the first term and capital S for the second term, where those both functions of x. And now I'm going to write out the definition of the derivative for that particular expression. The definition of the derivative says that the derivative is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And those are all the little f's. So in this expression, that will look like the limit as h goes to 0 of capital F at x plus h times capital S of x plus h minus capital F at x, capital S at x, all over h. Now, if I attempt to do the limit right here, I get 0 over 0. So I'm going to do more. And what I'm going to do is I'm going to add 0 to the numerator. But it's going to look like this. And then I got this term on the end. So I did a funky way of adding 0. You'll see why in a second. I added f of x plus h times s of x, and right in front of it, I took it out. And I did that so that I can group terms together. If I group these two terms together, I have a common factor of f of x plus h. If I group these two terms together, I have a common factor of s of x. And so I'm going to pull those common factors out and see if it fits right up in here. From the first two terms, I said I'm pulling out f of x plus h. And so the second factor will look like s of x plus h minus s of x. Then over here, I'm going to pull out the s of x, and I'll put it on the end. Inside, I'll have f of x plus h minus f of x times that common factor of s of x. Then all of this is divided by h. If all of it's divided by h, I can divide the individual terms by h. So I'm going to divide the first batch by h and the second batch by h. But I'm going to put it here and here. You can think of this as being over 1 and that as being over 1, if that helps any. And I did that so that you can look inside those parentheses here and see something that looks familiar. That's the difference quotient for s of x. That's the difference quotient for f of x. So when I do this limit, take the limit as h goes to 0 here, and I get capital F of x. Take the limit as h goes to 0 in this brackets, and I get what's called S prime of X. In here, I'll get F prime at X, and this doesn't depend on H. And what's left is the product rule. I'm going to write it like this. The derivative with respect to X of a first function times a second function is done one factor at a time. I hold the first one, take the derivative of the second one, then add to it the derivatives done the other way. The derivative of the first one, stop, times the second one. So it's, in words, first times the derivative of the second plus the second times the derivative of the first. Since they're added, you can do them in any order that you want. Hold one, take the derivative of the other, then add to it the expression done the other way. But I'll show you that it works with this one. I'm going to take the derivative of x squared times x cubed using the product rule and show you that it'll simplify to 5x to the 4th. So, product rule. The derivative with respect to x of x squared times x cubed is the first times the derivative of the second. So I took the derivative of x cubed and got 3x squared plus the second times the derivative of the first. And so I get 3x to the 4th plus 2x to the 4th for a grand total of 5x to the 4th. Of course, we'd never use the product rule on something that small. We'd use it on something bigger, something that we don't want to multiply out before we take the derivative. And soon we'll encounter functions that we can't multiply out. So this is what you've got to remember here. That's the product rule. The stuff that I did before, you don't have to remember. That stuff there, it's just the derivation. Get all this out of the way. Let's do an example. If I have two things multiplied together, and maybe they have a bunch of radical signs and stuff like that, and I don't want to mess around with simplifying that. I'd rather just leave things put. So for example, suppose I wanted to take the derivative of suppose I've got in the first factor the cube root of x plus 2 divided by x to the 4th, and I'm multiplying that with the square root of x plus, I don't know, x to the 100 plus 2. I could multiply that out if I wanted. It wouldn't take that long. But if I'm finding the derivative, why do that? Why not just go ahead and take the derivative? But as before you take the derivative, take a minute and rewrite the expression so that all of the x's are on top and with a fractional exponent, or with an exponent, not necessarily fractional. In this case, the radical signs are fractional. So I'm going to rewrite it as x to the 1/3 plus 2x to the -4. And the next one I'm going to write is x to the 1/2 plus x to the 100 plus 2. So here's my first factor, and here's my second. And so let's apply the product rule. It says leave the first one alone. Now take the derivative of the one next to it. So talk to me, what's the derivative of x to the 1/2? Good. Now the derivative of x to the 100. And then finally the derivative of 2. Yeah. So I'll just stop there. Now we go the other way, put your little plus sign in here. And now copy down the second factor before you took its derivative, x to the 1/2 plus x to the 100 plus 2. And now we're multiplying by the derivative of the two terms in the first parentheses. So here's where you come in, derivative of x to the 1/3. -2/3, gotcha. What about the derivative of 2x to the -4? Minus 8x to the -5. And it's probably good manners to write everything with positive exponents. We don't have to multiply it out. If we didn't want to multiply it out at the beginning, why would we want to multiply it out now? But just get back in the practice of writing with positive exponents. This is x to the 1/3, 2 over x to the 4th. This is 1 over 2x to the 1/2 plus 100x to the 99. And then this stays the same. Whether you use a radical or a fractional exponent, I don't care. But I do like to see things with positive exponents. And the one thing you just be careful with, it's only the x that has the exponent. So you leave the x's, you leave the numbers on top and move the x's down. Okay? It's this thing up here. This has a negative power, so it's going to go down to the bottom with the 3. The -8 stays on top, and the x to the 5th goes on the bottom. So anything with a negative power goes on the bottom. Okay? All right, the next thing is that I can't take the derivative of a fraction by taking the derivative of the top and dividing it by the derivative of the bottom. Let's look at a reason. Let's take, say, x to the 5th divided by x squared. Well, that's the same as x cubed. And I know the derivative with respect to x of x cubed is 3x squared. But if I take the derivative of the top term and then divide it by the derivative of the bottom term, I'm going to have a 5x to the 4th and a 2x, which gives me a 5x cubed over 2. So you see, you don't get the same thing. You can't take the derivative of a fraction by taking the derivative of the top divided by the derivative of the bottom. So note that if I have a top function and a bottom function, and I want to take the derivative of it, it's not equal to the derivative of the top divided by the derivative of the bottom. Absolutely not equal to. We've got something called the quotient rule, and I'm going to derive the quotient rule using the definition of the derivative again. You can watch that part. You don't have to write that second part down. You can just watch me do it. I'm going to do almost the same steps. I'm going to, somewhere in the middle, add a version of 0 so that I can do the factoring by grouping. So here's the derivation of the quotient rule. I'm gonna let f of x be written as a top function minus over a bottom function. And then I'm going to write the definition of the derivative, that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. So in this first slot, I'm going to put my top function and my bottom function both as functions of x plus h. Minus my top function over my bottom function, all divided by h. Now I'm going to get a common denominator. I'm going to multiply this first fraction by b over b, and this by b of x plus h over b of x plus h, so that they all have a common denominator. So this one over here, I said I'm going to multiply by b of x plus h over b of x plus h. So there's the common denominator. This is multiplied by b of x, that's multiplied by b of x plus h. So I still got to divide by h, but eventually dividing by h is going to be multiplying by 1 over h. So I'll just do that now. Now here's where I'm going to add 0, because again, if I try to take the limit as h goes to 0, I've got 0 over 0. So I'm going to add 0 with my red marker, like this. Keep this here. Let's see, I'm going to first subtract b of x times t of x. Then I'm going to add b of x times t of x. Okay, but I'm going to add it at the end. I'm going to take this now and I'm going to add it right here. And then I got all the other stuff still. So now I'm going to pull out the common factor and do some rearranging furniture. Between the first two, I'm going to pull out the b of x. Brackets here, and have t of x plus h minus t of x. Okay, then I'm going to here pull out my common factor of t of x, but I'm also going to pull out a minus sign. So if I pull out a minus sign, that's going to change that sign. So I've got my common denominator. I've got my 1 over h multiplied there. I'm going to choose to multiply it now. I'm going to send it through here, and it's going to distribute among the minus sign. I'm going to put it here and here, so we have our derivative terms. Now I'm going to take the limit as h goes to 0, and what's left is going to be your derivative. This is not affected by h, so it stays here. This is the difference quotient for the function t of x, so this becomes t prime of x. This doesn't have an h in it. The next one's the difference quotient for the bottom factor, so that becomes b prime of x. H goes, oops, this is not a t, that's a b. It's a b. As h goes to 0, this gives me the b of x times the b of x, which we're going to write as b of x squared. So that funny looking scheme is how you take the derivative of the top and the bottom. Let's try it with these two. I'm just going to copy it under there. So from our example, using this as the top and that as the bottom, I'm going to show you that we will get something that simplifies to the derivative of x cubed. So it says copy down the bottom, take the derivative of the top, so that's a 5x to the 4th, minus the top, times the derivative of the bottom, derivative of x squared is 2x, all over the bottom squared. And that should be the derivative with respect to x of x to the 5th over x squared. Let's see if it simplifies the way we want it to. X cubed times 5x to the 4th is the same as 5x to the 7th. X to the 5th times 2x is oh, that's a 6. I don't want that. And that bottom. Oops, I copied down x cubed here. That should be an x squared. My bad. But that sure does help. So now that makes that an x to the 6. Now here I get minus 2x to the 6th. And on the bottom I have an x to the 4th. And so I get 3x to the 6th over x to the 4th. Subtract exponents to simplify there. And there's the 3x squared. That is the derivative of x cubed. So it looks funny, but by gosh, it works. The quotient rule says you take the bottom times the derivative of the top, minus the top times the derivative of the bottom, divided by the bottom squared. So again, with the primes, it's easier to remember. Bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. And that's called the quotient rule. We need the quotient rule more than the product rule in most cases, because sometimes we can avoid the product rule by multiplying something out. But we really can't avoid the quotient rule. There's not always ways to simplify a fraction so that it looks like x's to a power added together. Cut me off again. So let's look at something like that. Let's take the derivative. Let's just put a 3x squared on top and an x squared plus 7 on the bottom. So algebraically, there's no way I can write that as anything but a fraction. I can't write that as a bunch of x to a powers added together. But I still can take the derivative of it with my brand new, hardly never been used quotient rule. And so here we go. Copy down the bottom, x squared. Well, I'm going to write the quotient rule out first. Bottom times derivative of the top minus top times derivative of the bottom over the bottom squared. Now here we go. Copy down the bottom, x squared plus 7. Now we multiply by the derivative of 3x squared. What do you think I should put here? 6x. Right? Bring the power down, raise it to 1 power less. Minus the top, 3x squared, and now it's your turn again, the derivative of the bottom. Just 2x. All divided by the bottom squared. Now we are going to simplify this because there is a such thing as the derivative of the derivative, something called the second derivative. If I wanted to take another derivative, I want this as simplified as I can get it. Now, one thing you can't do is cancel these just because they look alike. This bar acts as parentheses, and I've got two things subtracted. So I can't just pick my favorite term and cancel it out. It's not a common factor. So let's work above the bar and simplify this out by multiplying out the numerator. And I'll have 6x cubed plus 42x minus 6x cubed, all divided by x squared plus 7 squared. There's really not much reason to multiply the bottom out. So I'm going to just leave it like that. And then you see the 6x cubes add each other out. And I have my derivative simplified all the way down to 42x over x squared plus 7 squared. Now, if somebody did say, hey, take a derivative of your derivative, then I'd have to multiply the bottom out so that I have individual terms. Okay. Now, what I want you to get used to doing is not just stringing together equal signs. F is something different than F prime. So if I want to take the derivative of F on my next line, I label it as such. Now, the other equal signs make sense because those are still all F prime. Okay. For higher ordered derivatives, let's just start off with something like f of x is x to the 3 halves. Now its first derivative looks like 3 halves and then 1 power less. So 3 halves minus 1 is the same as 3 halves minus 2 over 2. So I get a 1/2 here. The derivative of the derivative is called the second derivative. And if I'm using the prime notation, I can just put 2 primes up here. And all I do is I take the derivative of this. So I'm going to take the 1/2 and multiply it with 3 halves and get 3/4. And then that's x to the negative 1/2. Because I took 1 away. My minus sign fell way the heck down, so let me pick it up a little bit. Bring the power down. That gives me the 3/4, 1 power less. The next derivative, we just keep on counting, that's the third derivative. I can put 3 primes here. So I take the negative 1/2 times the 3/4 and get a negative 3 over 8. Now I subtract 1 to give me a negative 3 halves. But from here on out, I don't keep lining up primes. I put a number in parentheses to denote the derivative. So this one has a 4th derivative. And we would write that with a 4 up here to keep you from thinking it's a power. And it's just the derivative of the third derivative. So I have a negative 3 halves times a negative 3/8 to give me a positive 9 over 16. And now I take another 1 away from there, and it gives me negative 5 halves. And I keep going and going and going and going. So that's how we denote it with the prime notation. If I'm using the dy over dx, if this is y, our first derivative is dy over dx. Our second derivative is d squared y over dx squared. We put the order of the derivative here. and then behind the x. So the third derivative would look like d cubed y over dx cubed, but again, it's not a cubed power, it's a derivative. This will be more used in your calculus 3 class because we're going to have functions of several variables, and then we have to tell you which variable to pay attention to. Okay? And so that's what you do in this section. You learn the product rule, the quotient rule, the basic derivative rules, and higher ordered derivatives. So let's see how you do on that, and then we'll talk about derivatives of sines, cosines, all the trig functions, exponentials and logarithms on Wednesday, and you'll let me know how you're doing. So practice a bunch of these and tell me on Wednesday how good or bad you feel about derivatives. Bueno? All righty. Look like I put you guys to sleep. Oh, let me give you your papers back. Back. You turn in the papers, stick around for a second. Let me get this to you. Let's see, Riley Mullen, Geraldine, Rebecca. I've got 2 different subdivisions. You want that one, that one. Aubrey Martinez, Timmy, Jordan. Oops. No, that one. You'll make me see 2 different distances. The rest of you are turning things in on the right. All good? Thank you. Okay, let's catch you off.